Good evening to all the respected teachers, our guests, to the second day of this session of Atal. Today, for the first session, we have with us Dr. AVILASH Prasad PANSARI. He has completed his Bachelor in Engineering in Electrical Engineering from UCE Burla in 2003. He has also completed Cost and Management Accountant from ICWAI Bhilai chapter in 2013. Sir has a job experience of 3 years in Jindal Steel and Power Limited from 2004 to 2007. Sir has a 1.5-year experience in Bakarao Steel Limited sale in electrical testing, and sir also have 15 years of experience in logistics in Bhilai Steel Plant. Sir has 3 years experience in finance in Bhilai Steel Plant. Sir is a runner-up in competitions, Chairman's Trophy for your manager in 2015-16. This is a prestigious competition within SAIL among all the steel plant of SAIL, which include RSP, BSP, BSL, DSP, SSP, and ISP. As a reward, apart from trophy from SAIL chairman, got a chance to visit Kobalco Steel Plant, Japan for 3 days. Sir is the winner in the same competitor in 2020-2021 and has visited to another foreign steel plant, India.
So now, Engineer Pansari, now you can start your session. So start your presentation.
Okay, thank you. Thanks for my briefing, sharing my briefing. And I am thankful that this opportunity is provided to me. Although I am not connected to the technical field since long, I will try my best to give insight of this topic, that is optimal scheduling of grid-connected microgrid with respect to my working organization. That is.
So please share your screen.
Yes. Is it visible now?
Yes, visible.
So I will try my best to give the insight of this topic, that is optimal scheduling of grid-connected microgrid with respect to my working organization, Bhilai Steel Plant, which is an integrated steel plant of SAIL. The milestone of today's journey is, first, I will tell about SAIL, then brief about my plant, Bhilai Steel Plant, material load flow of Bhilai Steel Plant, then the concept of optimal scheduling of grid-connected microgrid, electrical load flow of Bhilai Steel Plant, and microgrid of Bhilai Steel Plant and its linking with power grid. First, coming about SAIL. SAIL is incorporated on 24th January 1973. 24th January we celebrate as SAIL Foundation Day. Today is 21st. And after 3 days, we will celebrate our SAIL Foundation Day. We have many events. One of the major events we conduct is SAIL Run. SAIL has 5 integrated steel plants. The Bhilai Steel Plant, which I am working in, is in Chhattisgarh. It produces a rail of 13 meter and 26 meter lengths, long rail of 260 meter length, on which Indian Rails travels. We produces bloom, billets, slabs, channels, joists, angles, TMT rebars, wire rods, crane rails, plates, pig iron, and coal chemicals. Durga Steel Plant, another integrated steel plant, is situated in West Bengal, and it produces bloom, billet, joist, narrow slabs, channel, angles, TMT rebars, wheel and axle of railway, pig iron, and coal chemical. Rourkela Steel Plant, which is in Odisha, it produces plate mill products, HR plates, HR coil slabs, CR sheet, coils, galvanized sheets, which is in the form of plain and corrugated both. ERW pipes, spiral weld pipes, CR canoe, pig iron, coal chemical. Bokaro Steel Plant, which is in Jharkhand, It produces HR coils, slabs, HR sheet, plates, CR coils, sheets, GP sheets, CG sheets, galvanized steel, HRPO, pig iron, coal and chemical. And ISCO steel plant, which is situated in West Bengal, it produces wire rod, bar and rebars, joists, channels, angles, bloom billets, universal special sections, jet bar, MS arch, pig iron and coal chemical. We have ferrous alloy steel plant at Chandrapur, Maharashtra for ferromanganese and silicomanganese. We also have 3 special steel plants. One is at Salem Steel Plant, Tamil Nadu, which produces cold rolled stainless steel, hot rolled carbon and stainless steel products, and microalloyed carbon steel. We have alloy steel plant in West Bengal, which produces alloy steel squares and rounds, wear resistance plates, forging, crane wheels, forge rolls plates, special quality slabs, and stainless steel slabs. And in the Visvesvaraya Steel and Iron Steel, in the Karnataka, we produce high quality rolled and forged alloys, special steel products. Apart from this, SAIL has our subsidiary for refractory production, that is SAIL Refractory Company Limited, SRCL. SAIL has 5 central units, that is Central Marketing Organization for marketing, Center for Engineering Technology for designing engineering, Research and Development Center for iron and steel for research activities, SAIL Consultancy Organization for outside consultation, Environment Management Division, and our Management Training Institute, which is situated at Ranchi, which provided our enhanced and basic trainings. We have joint ventures for power production and utilization. One is with NTPC and SAIL Power Company Limited, which is called NSPCL. In NSPCL Rourkela, there are 2 units of 60 megawatt each. In Durgapur, 2 units of 60 megawatt each. And in Bhilai, 30 megawatt 2 units and 14 megawatt 1 unit. We have also BPCL, Bokaro Power Supply Company Limited, which is in joint venture with Damodar Valley Corporation for 338 megawatt generation. And SAIL joint venture others are Metal Junctions, SAIL and Moil Ferroalloys Limited, International Coal Venture Private Limited, SAIL Rights, Bengal Wagon Industries Private Limited. To understand SAIL more, let's see a short video on SAIL.
SAIL, at the forefront of nation building. Steel Authority of India Limited, an organization that tests your mettle at every step, an employer that challenges you each and every day, surprises you each moment, and teaches you something in every passing moment. A behemoth with a turnover of more than rupees 1 lakh crore, SAIL is a leader in the Indian steel industry, having a pan-India presence. Projects that had earlier remained unimaginable have been made possible with SAIL Steel, be it steel for the Statue of Unity or the thousands of kilometers of rail tracks connecting the country, the formidable INS Vikrant, or the longest bridge in the country, Dola Sadia. We are known to have the best technical and managerial talent in the country. Men and women who are always ready to take on the different challenging assignments that they encounter with dedication and passion. SAIL's engineers in disciplines like mechanical, electrical, metallurgical, chemical, electronics, computer, IT, mining, etc. redefine steel making each day. The limits of technical knowledge and acumen of new recruits are tested time and again. Needless to say that the talent at SAIL always shines through. Every unit in SAIL is like a huge factory in itself, with captive power plants, foundries, and huge shops, the giant scale of which is totally unimaginable. Many do not know that SAIL is also the largest iron ore miner among steel-producing companies operating mining units spread across mineral-rich states in the country. Many would not even know that the quantity of the various byproducts generated at SAIL plants is so humongous that they are used as input materials in different chemical and fertilizer industries. The enterprise resource management projects such as SAP have been implemented in the company across its units which has modernized and revolutionized the company's operations. These and similar systemic improvements are slowly leading us to the vision of Index nightmare for others with effortless ease, right from getting coal from Australia to supplying steel products to almost every district of the country. SAIL does this with smile and the contentment of contributing to the nation's growth. Steel Authority of India Limited. There's a little bit of SAIL in everybody's life.
It is a brief video of our SAIL as a whole. Now coming to my integrated steel plant, it is Bhilai steel plant. I want to share a short video of it. Just a couple of seconds. It is about my integrated steel plant, Bhilai steel plant.
Bhilai Steel Plant, 11 times winner of the Prime Minister's Trophy for Best Integrated Steel Plant in the country. SAIL's flagship is proud of providing the best and desired grades of steel for the nation. Supplier of the world's longest 260-meter rails to the Indian Railways, Bhilai Steel Plant also produces best quality plates and high-strength TMT bars, wire rods, and merchant products. From a capacity of 1.4 million tons, SAIL Bhilai Steel Plant's journey continues. To meet India's growing demand for steel, the plant has brought in new and modern units as part of its 7 million ton modernization and expansion program. The new MODEX units commissioned include coke oven battery 11, blast furnace 8, universal rail mill, bar and rod mill, steel melting shop 3, an additional sinter machine in SP3, besides associated new units including ore handling plant A and B, RMP3, power and blowing station number 2. With such cutting-edge technologies incorporated, Bhilai Steel Plant is producing wider range of special grade steels with superior quality to meet India's fast-growing demands in infrastructure, defense, and other sectors. Let us take a peep into SAIL Bhilai's MODEX units. Named after goddess Mahamaya, popularly believed to have blessed Chhattisgarh with prosperity, blast furnace 8 has a useful volume of 4060 cubic meter and an annual capacity of 2.8 million ton per annum. It can produce over 8,030 tons of hot metal every day. Hot metal obtained from blast furnace 8 is converted and refined into crude steel of the desired chemistry at the new and modern SMS3. For this, SMS3 has a basic oxygen furnace, continuous casting plant, and secondary refining units. SMS3 is equipped with 3 converters of 180-ton capacity, 2 billet casters, and 1 blue caster. Secondary refining units comprise of ladle furnace, RH degasser, and argon rinsing station. Blooms from SMS3 are rolled into the world-class rails at the modern Universal Rail Mill. With a capacity of 1.2 million tons per annum, Universal Rail Mill rolls out the world's longest 130-meter length in single piece and 260-meter long welded rail panels. The mill is equipped with a modern rail welding plant. Whether it is the length, grade, or quality, Bhilai Steel Plant has been fulfilling the requirements of Indian Railways for more than 6 decades now. Not only is BSP supplying the world's longest rails, the plant is also producing asymmetric rails, R260 grade rails, as demanded by Indian Railways, and is now prepared to produce head-hardened rails. One of the world's largest producer and supplier of rails, Bhilai Steel Plant has been supplying world-class rails to Indian Railways as per specifications of quality, grade, profile, and length. Indian Railways, that is modernizing itself and moving towards faster rail transportation with higher axle loads, has been demanding micro-alloyed rails from SAIL. To fulfill this requirement, a new grade of rails named R260 with new 60E1 profile developed by SAIL Bhilai is now being rolled out and supplied to Indian Railways. This new grade of rails with specifications that are even more stringent than European specifications are suitable for high-speed trains and higher axle loads. Committed to supply world-class rails that are of the best quality, SAIL Bhilai takes utmost care at every stage of production. The hydrogen content in rail steel has been kept at below 1.5 ppm, which by itself is a world benchmark. Each and every rail produced is subjected to a range of tests, including online NDT testing, ultrasound and eddy current testing, laser straightness measurement system, computer-controlled automatic rail handling system, and yard mapping for storage of rails. Today, Bhilai claims with a great sense of pride that the nation runs on SAIL Bhilai rails. Interestingly, the volume of rails produced so far, if laid in a single line, can encircle the globe 14 times and can even reach the moon. Steel is one of the most important components of any construction activity. As such, when we talk of the infrastructure sector, the quality of steel used is a deciding factor. SAIL Bhilai's bar and rod mill has been designed to meet exacting demands of customers in the infrastructure segment. The new and modern mill with 0.9 MTPA capacity rolls out a wide variety of TMT bars and wire rod coils with sections ranging from 5.5 mm to 60 mm. The superior quality of products with consistent mechanical properties and good weldability has been widely appreciated by customers of SAIL Bhilai. Bar and rod mill that rolls billets obtained from SMS3 into finished products is equipped with such state-of-the-art technology as automatic digital type walking beam furnace and facilities for high-speed rolling. BRM's products that include SAIL secure TMT bars are fast becoming the first choice of builders. Several new units have been installed as part of Bhilai Steel Plant's MODEX program to support the new production shops. These include the 7-meter tall coke oven battery 11 that supplies coke to blast furnace 8. The second machine of sinter plant 3 meets the additional sinter requirement to sustain higher levels of hot metal production. The refractory material plant 3, with a 450 ton per day capacity, has 4 kilns to produce lime and 1 kiln to produce calcined dolomite, which are used by SMS2, SMS3, and SP3. Ore handling plant A and B are playing a crucial role in supply of enhanced volumes of raw material. Several new projects at the plant's Dalli mines are helping meet iron ore requirement to sustain 7 million ton crude steel production levels. These include slime beneficiation plant to utilize low-grade ore. The plant has recently begun mining from newly developed Dulki mines. A pellet plant is also being installed to utilize available stocks of iron ore fines. Significantly, the plant has recently started getting iron ore from its Raughat mining project. Being set up for the plant's future raw material security, Raughat has huge reserves of good quality iron ore. Work on the Rajara to Raughat rail line is fast progressing. With rail services already begun up to Antagarh, SAIL Bhilai is now getting ore from Anjrail block near Antagarh as part of its interim mining plan in Raughat. Mining in what has been a region affected by Naxal activities has been a challenge. BSP has built inroads in this difficult region by carrying out CSR activities on a large scale. These include extending medical facilities in remote areas, providing good school education, building rural infrastructural facilities, etc. BSP has been supporting scores of tribal girls for their nursing education in Bhilai. BSP has also been imparting ITI training to the rail line displaced persons and then giving them employment. By carrying out such CSR activities and also helping set up the rail line, BSP has not only won the hearts of the local population, but has also facilitated development of the region. SAIL Bhilai Steel Plant has not only strengthened the sinews of the nation by providing the desired quality and volumes of steel to accelerate infrastructural development, it has also positively impacted society by transforming lives through its CSR activities. One recent example is the consistent supply of liquid medical oxygen to save lives in various parts of the country during the COVID crisis. Winner of the Prime Minister's Trophy for Best Integrated Steel Plant in the country, as many as 11 times, Bhilai Steel Plant also has the distinction of having the maximum number of Shram Ratna awardees and hundreds of Vishwakarma Puraskar winners. The plant also has won several awards in various parameters like energy efficiency, quality, environment protection, safety, and CSR. Rails produced by SAIL Bhilai Steel Plant crisscross the length and breadth of our country. Steel produced by Bhilai is used to build the Indian Navy's aircraft carrier and other warships. Steel rolled in Bhilai is used in satellite launch vehicles. Steel produced by Bhilai is used for high-rise buildings and industrial structures in seismic and corrosion-prone areas. When it comes to building important projects of national importance, such as big power and irrigation projects, roads, flyovers, bridges, and tunnels, it is steel produced by SAIL Bhilai that is used and sought for. SAIL Bhilai Steel, steel that India trusts.
That is about my plant, Bhilai Steel Plant, the Indian rail on which which Bhilai Steel Plant produced, Indian rails travel on that. Now, before moving to the electrical part, let us have some idea about the raw material flow of Bhilai Steel Plant so that the understanding further will be easier to us.
Mr. Pansari, so is there audio in this video or not?
Yes, sorry.
So audio is not coming.
Audio is not coming. Okay, I think we should switch to the PPT part then.
Okay,
I'll
okay.
stop sharing it. Again, sharing my PPT. Prior to that video is okay? Audio and video,
So that was okay.
Okay.
Both audio video enabled.
Okay, let me share the PPT now then. This PPT is visible?
Yes, it is visible. Screenshot पे.
Yes, sir.
And dear participants, so for a short duration, all of you please switch on your video so that we can take one screenshot, then you can mute. So all the participants are requested, so please switch on your video. After taking the screenshot, then you can mute.
Shall I start now?
Just wait. Okay. Thank you, dear participants. Now you can mute your video. And Mr. Pansari, you can continue.
Okay, coming toward the concept of the grid connected microgrid. A microgrid is a group of interconnected loads and distributed energy resources that acts as a single controllable entity with respect to grid. It can connect and disconnect from the grid to operate in grid connected or island mode. Microgrids can improve customer reliability and resilience to grid disturbances. It is hanging. I'm stop sharing and again sharing it. It is hanging somewhere between. Yes, it is not okay. Then optimal scheduling of grid connected microgrid. Grid connected microgrid optimal scheduling is a method for optimizing the operation of a microgrid that is connected to a power grid. It is an important part of the smart grid optimization and can help to reduce energy consumption and environment pollution. This is a small schematic diagram of grid connected microgrid where a hospital is connected with the wind power to a DC generator and a grid system, microgrid system. The benefits of it is reduced energy consumption, that is optimal scheduling can help to reduce the amount of energy a microgrid uses. Reduce environmental pollution, optimal scheduling can help to reduce the amount of pollution a microgrid creates. Improved economic benefits, optimal scheduling can help in improving the economic benefits of a microgrid. Again, photovoltaic panels and its diagram for a solar power microgrid, where a AC circuit breaker is there for household sockets and electrical meter to connect it with the grid. Then if we come to grid connected DC microgrid, a grid connected microgrid, DC microgrid is a local electrical system that connect to and disconnect from the main power grid. It can operate in grid connected mode, which improves a constant power supply, or in island mode, which allows it to operate independently. DC microgrid can use power panels to generate electricity, which is then shared with the main electrical grid. It can also include other renewable sources such as wind turbines, and energy storage systems such as batteries. How it works: part of a DC microgrid, solar panels, which convert sunlight to direct current electricity, DC-DC converter, which processes the energy from DC sources, DC-AC inverter, which connects the DC microgrid to main electrical grid, and the batteries, which can be used to store energy and balance supply and demand. Again, a schematic diagram of it. The benefits of a DC microgrids are: DC microgrids can be used to meet increasing demand for electricity. They can be used to integrate a large amount of solar energy. They can be used with a variety of electrical devices and loads. And the challenges here in it is integrating a DC microgrid with an existing AC network can be difficult and expensive. And local production methods can be affected by system topology and intermittent renewable energy sources. Further challenges are integrating a DC microgrid with an existing is difficult and expensive. It is the same. DC microgrid versus AC microgrid. In DC microgrid, common DC bus is used to connect the grid through an AC-DC converter. The operation principle of a DC microgrid is similar to AC microgrid compared with AC microgrid. DC microgrid is a good solution to reduce the power conversion losses because it only needs one power conversion to connect to DC bus. How it works: grid connected mode, the microgrid is connected to the main power grid and can import or export electricity. In the island mode, the microgrid is disconnected from the main power grid and operates independently. This mode can be used during grid failures or in remote areas. Advantage of grid connected microgrid system: a grid connected system without batteries are the simplest and cheapest solar power setup available. And by not having to charge and maintain the batteries, they are also more efficient. It is important to note that a grid-connected solar power system is not an independent power source, unlike a standalone system. Advantage of solar photovoltaic system: regards to all aspects, living with a grid-connected solar PV system is no different than living with just the normal grid power, except that some or all of the electricity that is consumed comes from the sun. PV solar system designed for grid connections are usually designed to meet at least half of a home owner's electrical needs. The advantage of a grid connected PV system, either with or without storage batteries, is that on clear blue sunny days when the photovoltaic system is producing large amount of current and the home is consuming low energy level, for example, if you are out of the home all the day working, your solar system keeps generating electricity. The excess electricity generated does not go to waste, but is fed back to the power grid to be used by the neighboring homes, who unknowingly end up using the clean renewable energy themselves while making money for you through your net metering arrangement. In a nutshell, solar microgrids are a step towards sustainable energy future. They can help to reduce greenhouse gas emission and contribute to the fast fight against the climate change. They can be installed quickly and efficiently, making them ideal for emergency situations. They can help to promote local development and empowerment. They can help in enhancing the energy resilience. They can help to reduce carbon emission. They can help to provide reliable power in remote or undeserved areas. It is a news clipping of our ISCO steel plant, which is in Burnpur, on 22nd Jan 2024. We have installed a 4 megawatt floating solar power plant. It is first ever in SAIL. After that, in our Bhilai steel plant, a 15 megawatt floating solar power plant is going to commission. It is under progress. The solar power plant, which is connected to the microgrid in ISCO, is reducing the carbon emission of ISP by 5,452 tons per annum. Now coming back to my plant, that is Bhilai steel plant, and the role of electrical section is generating electrical power, supply power to auxiliary loads, provide proper illumination and enabling supply, supply power to substation, electrics of electrostatic precipitator, instrumentation supply, electrics of lifting equipment, DC supply system, PLC SCADA system, AC, AW ventilation supply system. Now in the screen is the electrical load flow of Bhilai steel plant. We will cover one by one, which is relevant to us. First, the area which is blinking is Chhattisgarh State Electricity Power, from which we are connected with the grid. We are drawing power from there, and also connected is the NTPC SAIL joint venture PP3. This is 220 kV line. Our gross BSP load is 260, around 265 megawatt, and our township load is around 17.5 megawatt. The area blinking is showing the parameter. Now coming towards our in-house generation, that is PP2, it is again joint venture with the NTPC, where we have 3 turbines. Here parameter is showing 0. It is for some mistake, but the TG1 and TG2 is of 30 megawatt, and TG3 is of 15 megawatt. They are connected through grid in 132 kV, that is step up transformer of 11 kV to 132 kV. In the figure, you are showing various words like MSDS, that is main step down substations, and it is connected with the grid with various step down transformers. Now coming to another generating station, that is BPTG. Actually, it is connected with our Coco 1 battery. In the video, we have seen the Coco 1 battery, where we convert coal to coke through quenching, and in this process, various heat is being generated, and we use this heat to boil the water for steam generation inside the boiler. And the capacity of BPTG turbine is 14 megawatt. The make of the TG1, TG2 and TG3 is shown previous is of Russian make, and this BPTG is of Mitsubishi make. Now coming to the TRT, TRT is generation is of TRT 14 megawatt. Sorry, TRT is of 14 megawatt and BPTG is 4 megawatt. And TRT, in the TRT, we use the kinetic energy of the blast furnace gases. Blast furnace gases, we use the kinetic energy to rotate the turbine, and we generate 14 megawatt of the power. These are all connected through the step-up transformer of 11 to 132 kV through our various substation of MSDS. Now coming to the main part of our captive power plant, which is called as PP1, where we have 5 generators, TG0, 1, 2, 3 and STG4. The capacity of 0, 1, 2 is 12 megawatt each, and for 3 it is 15 megawatt. TG0, 1, 2 is a Russian make and TG3 is BHEL make. And here we generate 6.6 kV, and it is our for captive power plant, which is connected with the grid with the tie line. You can see here it is written as TL1, TL2, TL3, and through this tie line, transformer is connected, step up transformer 6.6 kV to 132 kV, and again it is connected to grid with the help of MSDS. Further, coming to detail about this captive power plant, the total power generation through this captive power plant is 51 megawatt, is contributed, as said earlier, it is contributed by TG0, 1, 2, 12 megawatt each, that is 36 megawatt. The rating is 12 megawatt, 6900 volt, 50 hertz, 3 phase. Excitation is rotating exciter. TG3 is 15 megawatt, rating 15 megawatt, 6.9 kV. 50 hertz, 3-phase, and excitation is brushless excitation. The total generation is 51 megawatt. Our base load is 35 megawatt, and floating load is 16 megawatt. So floating load is sent to MSDS1 through tie lines 1, 2, and 3, which I have shown earlier. Synchronization of the generator. The condition is, again, what we have studied in the book, that is equal phase sequence, equal voltage, and equal frequency. Now it is shown through the diagram. The first is CSCB grid, which is connected with the MSDS1, whose frequency is 6.9 kV and 50 Hz. And our MSD is the main synchronizing generator section 1, where if the TG1 is not operating, then it is 0 kV and 0 Hz. And if it starts with rotating 48 Hz, and if we will give excitation and increase the excitation, 1 kV, 2 kV, 3, 4, 5, 6. And if we will try with the 6.6 kV and we want to synchronize it by giving the close command, it will not synchronize as the frequency of the grid is 6.9. Then we have to again increase the excitation and hence frequency to 6.9. And if we will give the command, then it will connect the tie line and we will connect it with the grid. This synchronization of TG turbo generator 1. Now coming to the load shedding and islanding of the captive power plant, which I have shown. It is necessary because there is a trend towards the large site generators, a large distance between the load centers and generation, large power system networks, and because of which there is instability due to loss of machine and tripping of line. So solution is load shedding and islanding. Load shedding, load generation mismatch causes variation in frequency. Last mismatch is result in slow change in frequency and will result in self-stabilization of frequency. And large mismatch result in fast change in frequency, rapid fall and increase of frequency. If we will show through the diagram that if our generation is 100 megawatt in a frequency of 50 hertz and load is 100 megawatt, and suddenly it gets increased, then automatically frequency starts falling to match the load, and ultimately it reduces to match the load and it gets stabilized. Similarly, if there is a load generation mismatch due to decrease of load, then again there is a tendency to increase the frequency to balance the load. And it got stabilized when the load got balanced. The load shedding rate of fall of frequency depends upon the percentage overload, inertia of power system, and load reduction ratio. Salient feature are response as per system requirement, and speed operation should not be too fast to avoid malfunctioning. Load shedding should not be sluggish to prevent the total collapse of the system. It should be in order of the criticality of the loads. So we have our scheme 1 at generating station, that is load is divided into 4 groups, that is group 1, 2, 3 and 4 as per the criticality. And the formula for the loads to be set is P upon P plus 1 into 1.05 to 1.1 PU. For example, if overload is 0.6, then the load shedding is 0.42 or 42%. We have divided the total load to be shared in 4 groups, that is 1, 2, 3 and 4. Group 1, the load of the group 1 who are in the range of 48 Hz to 0.5 second delay will shed it first. Then group 2, that is in 1 second delay for 47.7 Hz to 0 delay in group 3 and 47.5 Hz in 0 delay in group 4. And there is a backup timers. Through diagram, if there is a 50 Hz generation and suddenly frequency falls to 49.6, you can see the group 1 is 48 Hz. If frequency falls to 48 Hz and time elapsed is 0.5 second, Then the group 1 got shaded. Now time is 0, 0.1, 0.2, 0.3, 0.5. Then automatically group 1 got shaded. The load of the group 1 connected with the group 1 got shaded. So we accordingly do the logistic that which load can be shaded if this type of situation occurs. Similarly, if further frequency reduces for more time, that is for 1 second, then the load which are connected in the group 2 got shaded. If the frequency further falls to 47.7, then the loads of the group 3 got disconnected. Similarly, for group 4, 47.5 Hz, then group 4 will be shaded. The load shading scheme's drawback of the load shading scheme is that non-selective tripping if frequency falls rapidly. At the rate greater than 0.3 Hz per second, group 3 load shading occurs before group 2. And if it is at a rate of 0.6 Hz per second, then group 3 load shading occurs before group 1. So there is an alternative load schemes too. Then how to overcome these drawbacks? We have devised an alternative load setting scheme, that is 2, where we use the rate of change of frequency relays with scheme 1, that is group 1. In this scheme, group 1, if there is 48 Hz, frequency drop to 48 Hz, 0.5 second, or at the rate of 0.6 Hz per second, and frequency is below 48.2 Hz. In the group 2, frequency 48 Hz, 1 second, or rate at the greater than 0.3 Hz per second, and frequency is below 48.2 Hz. Through diagram, it can be understood. Group 1, 48 Hz, what I have shown. Group 2, 48 Hz, 1 second. df by dt is greater than 0.6 Hz per second. Group 3, 47.7, and group 4, 47.5. So advantage of this scheme is that there is no change in tripping sequence and load shedding occurs faster than the scheme 1 and system recovers. So in our PP1, what is we call as captive power plant, in the group 1, 47.5 Hz, we have 3 substation. We have connected this substation for shedding at first instance, that is SMS1, which is called substation 16, CAS2, that is compressed air station 2, that is substation 18, and OP2, oxygen plant 1, that is substation 16. In the group 2, that is 47.2 Hz category, we have substation of BF, that is substation 3, 14 and 35, and SMS1, that is substation 5. Just a second. Sorry for the interruption. Now coming towards the islanding, that is acting as a microgrid. When our captive plant act as a microgrid, what is the network decoupling or islanding? Isolation of industries having an internal generation from grid and splitting of power network into independent subsystem, that is islands. Islanding in industries, as of we have PP1, we have 3 generators, 0, 1, 2, 3, and loads are connected to it. And we are grid, various loads are connected to the grids. And we are connected with captive power plant is connected to with the grid with the tie line. Islanding, why islanding of the industries have internal generation is necessary to save the generators from effective excessive under over frequency. Yes, whatever if there is a over frequency or under frequency that may get damage our load or our connected motors. So it is necessary to prevent the total collapse of the internal generation during grid failure. If there is a grid failure, then which our critical equipment should run. Otherwise, there is a collapse of whole system. Islanding technique, plane under frequency and negative rate of change of frequency relays, and plane over frequency and positive rate of change of frequency relays. Sensing low voltage and rate of change of voltage, sensing of frequency and direction of current flow. Islanding in utility network, carry out system study, identify subsystem and decide the relay setting. Suppose we do a case study. So suppose there is a case one where PV1 is normal running in synchronization with the grid, and generation schemes are adopted following outgoing feeders and their loads are restricted. Suppose we have, as we said, we have 4 generators and single generator is running. Then generation maintained up to 12 megawatt, TZ0 and TZ12 should be running. Loads of PP1, auxiliary and outgoing 6 MSG COCO1, 8 MSG PH, 22 MSG PH are restricted below 12 megawatt. These are some locations or loads which are restricted below 12 megawatt. Two generator schemes where generation is maintained up to 24 megawatt, TZ0, 1, 2, 3 and should be running. Loads of PP1, that is auxiliary 1, 2, 3 and outgoing is 5 MSG OH, 6 MSG COCO1, 8 MSG PH, 22 MSG. These are the names of the different loads are restricted below 24 megawatt. And three generator schemes, generation mentioned up to 36 megawatt, TZ0, 1, 2, 3 should be running. Loads of PP1, EF 1, 2, 3, 7 MSG, 19 MSG, 28 MSG, and outgoings that is 6 MSG COCO1, 8 MSG PH, 22 MSG PH, 5 MSG open earth, 17 MSG open earth, 18 MSG blast furnace, 21 MSG blast furnace, 32 MSG blast furnace, and 23 MSG oxygen plant BF8 are restricted below 36 megawatt. These are the different schemes we have adopted. If the load, we have our 3 generator are running in some, suppose 1 generator is running, 2 generator are running, and 3 generator are running. This is a tabular form. Suppose it is a case 2 where suppose there is a grid got failed. During the grid failure, islanding mode, PP1 will get desynchronized. That is, tie line 1, 2, and 3 will trip on df by dt. And power supply from PP1 will be available to the critical loads of different shops as followed depending upon the prevailing generation schemes at the time of failure. The critical, suppose if you will see the last 3 rows where permitted load per megawatt PP1 generation scheme, if there are 3 generators are running, then we have 36 megawatt of load in which we run our pump house 22 MSC and 8 MSC for 12.90 megawatt. We will give 2.9 megawatt to our COCO1, that is substation 1, 6 MSC. We will give 5.08 megawatt to our blast furnace, that is substation 3, 14 and 35, that is 18 MSC, 22 MSC and 21 MSC. We will provide 3.80 megawatt to steel melting shop, that is SS5 and 16, that is 17 MSC and 5 MSC. And we will give 3.04 megawatt to BF8 via oxygen plant, that is 23 MSC, substation 56 via substation 6. And we will give 9.50 megawatt to our PG auxiliary unit, that is AF1, 2, 3, that is 7 MSG, 19 MSG, and 28 MSG. If we are running on 2 generator scheme, that is, we are generating 24 megawatt through our captive power plant, then we will give 8.11 megawatt to power pump house, 2.47 megawatt to our COCO1, 2.66 megawatt to blast furnace, 2.38 megawatt to steel melting shop. We will cut the power to oxygen plant and we will give 8 megawatt power to PG auxiliary units. If we are running on single generator scheme, that is 12 megawatt, then we will give power of 4.84 megawatt to pump house, 0.48 megawatt to COCO1. We will cut the power supply to blast furnace, steel melting shop, and oxygen plant, and we will give 7.50 megawatt to our auxiliary units. This is how we have designed our load distribution system according to the captive power generation if grid fails, and we have to manage with our captive microgrid this load so that uh, the process should not stop. At least process should alive. Setting of the islanding tie lines are over frequency setting is 52.1 Hertz. Under frequency setting is 47.72 Hertz. df by dt setting is 47.9 Hertz and 51.5 Hertz. 0.3 Hertz per second and 1 second delay. That's much from my side. Thank you.
So, dear participants, any queries?
If there is time, we can see the video earlier, which is stopped.
Yes, sir, we can show it now.
Okay, let me try again. Is it now okay?
So, audio from the video is still not coming.
Video screen is not coming.
Video is coming, but audio is not coming.
Is it coming now?
No.
Let me share again from scratch. Is it audible now?
No.
No,
So
slight
let it
interrupts are there is no voice.
So maybe there is some problem with this video.
so let it be completed.
Okay.
Sir, one question with this, sir, from my side.
Yes.
Sir, can I know what is the electricity consumption per 1 ton of steel production?
I have to see this because in this manner we have not calculated it, but during the rate calculation it must be there. I will check it and revert it back.
Okay, sir. So I think that if there will be any resorts to reduce that electricity consumption per ton
No,
of.
no, no, it must be there because I am in finance and we calculate it.
Okay.
So the costing section do it. So I will
Yes, sir.
do the study that for
Okay, sir.
1 ton of hot metal production, how much electricity is needed and what is the expense of it. Definitely, I will get this data and revert back to you.
Okay, thank you, sir.
Thank you. I think in the video very much load flow got clear.